Welcome to this lecture on research methodology. Today, we are diving into a foundational topic, the need for research design. If you have ever wondered how scientists and researchers ensure their findings are actually true and not just random guesses, you are in the right place. We will explore why jumping straight into data collection is a terrible idea and how a well-thought-out plan acts as the master blueprint for any successful scientific inquiry. Let us get started. To begin, imagine trying to build a massive, beautiful house without any architectural blueprints. You might just start laying bricks randomly, hoping a kitchen or a bedroom naturally forms out of the chaos. Very quickly, you would run out of money, the walls would be crooked, and the roof might eventually collapse. Conducting research without a research design is exactly like building a house without a blueprint. You might collect a mountain of data, but without a plan, that data will be messy, useless, and confusing. A research design is your master blueprint that tells you exactly what to do, when to do it, and how to do it. Now that we understand the intuitive analogy, let us look at the formal definition. In academic terms, a research design is the conceptual structure or framework within which research is conducted. It constitutes the formal blueprint for the collection, measurement, and analysis of data. Think of it as a detailed, step-by-step strategic plan that outlines exactly how you will answer your specific research question. It dictates the type of study you are doing, such as whether it will be descriptive, experimental, or analytical. Furthermore, it specifies the exact methods you will use to gather information, the population you will study, and the statistical tools you will apply to analyze the results. With the definition clear, we must ask, why is this concept so absolutely critical in the real world of science and business? First and foremost, a good research design maximizes reliability and minimizes bias, ensuring that your findings reflect the truth rather than your personal opinions. It acts as a safeguard against wasting precious resources, such as time, money, and human effort, by preventing you from collecting irrelevant data. In fields like medicine or engineering, a flawed research design could lead to dangerous drugs being approved or bridges collapsing because the underlying data was fundamentally flawed. Additionally, it provides a clear roadmap for the researcher, reducing confusion and keeping the project strictly on track. This theoretical importance leads us to a mathematical representation. While research design is largely a planning concept, we can mathematically represent its primary goal, maximizing the efficiency and accuracy of a study. We define a conceptual formula for research efficiency, denoted by the letter E. E equals V times R divided by C times T. Here, V stands for the validity of the data, meaning how accurately it measures what it is supposed to measure. R represents reliability, which is the consistency of the results over time. In the denominator, C represents the total financial cost, and T represents the time taken. To get highly efficient research, we must maximize validity and reliability while minimizing cost and time. Let us see this formula in action with a concrete example. A university student is conducting a survey on student stress. Without a research design, her validity score is 40 and her reliability is 50. The cost is $200 and the time is 50 hours. We substitute these initial values into our formula. The numerator represents the total quality score, which is 40 times 50, giving us 2,000. The denominator represents the total resource expenditure, which is $200 times 50 hours, giving us 10,000. Dividing the quality score by the resource expenditure gives us an initial research efficiency of 0.2. This very low score indicates a lot of resources were wasted for little reliable data. Now that we have seen the chaotic approach, let us calculate the efficiency after she takes a methodology class and creates a strict research design. Her new validity becomes 90 and reliability becomes 80, while the cost drops to $100 and time drops to 20 hours. We substitute these improved values into the formula. The numerator, representing quality, is now 90 times 80, which equals 7,200. The denominator, representing resources, is now $100 times 20 hours, which equals 2,000. Dividing the new quality score by the new resource expenditure gives us a research efficiency of 3.6. This final answer shows a massive improvement over the initial score. Having calculated both scenarios, we can now mathematically prove the value of the research design. We want to establish exactly how much the student's efficiency improved. By taking the new efficiency score of 3.6 and dividing it by the old score of 0.2, we get an improvement factor of 18. By simply planning ahead with a research design, the student increased her research efficiency by 18 times. This proves mathematically that a good design yields much better data for significantly less money and time. Hard work alone does not guarantee good results. Structured planning is what multiplies your effort. This massive improvement in efficiency brings us to another critical mathematical concept: minimizing errors. In any study, the total error is the sum of sampling error and non-sampling error. The formula is simple. E sub t equals E sub s plus E sub n. Sampling error is a fixed statistical reality when you survey a subset of a population. However, non-sampling error represents human mistakes, poor data collection, and general chaos. A strong research design specifically targets and reduces this non-sampling error. When non-sampling error decreases, the total error of the entire study decreases, bringing your results much closer to the absolute truth. Let us apply this error formula to a specific case. A researcher is conducting a study and has a fixed sampling error of 15 units. Without a research design, poor data collection causes a massive non-sampling error of 45 units. We use the basic addition formula for total error. We simply add the initial sampling error of 15 to the initial non-sampling error of 45. This simple addition gives us a total initial error of 60 units. This high level of error means the research results are likely inaccurate and completely untrustworthy. It shows exactly what happens when a researcher collects data without a clear, structured plan. Now, let us see what happens when we introduce a structured plan. By implementing a research design, the non-sampling error is reduced by 80%. First, we calculate 80% of 45, which is 36. We then subtract this massive reduction from the original 45 units, dropping the non-sampling error down to just 9 units. Finally, we add the fixed sampling error of 15 to our newly reduced non-sampling error of 9. The final total error is now only 24 units. This step highlights how a good blueprint directly targets and eliminates human error during the research process. So, we have proven that the error drops significantly. Let us look at the mathematical reasoning behind this shift. We started with an initial total error of 60 units, driven largely by chaotic data collection. By introducing a design, we brought the total error down to 24 units. This is a huge improvement. Physically, this means the research is now much closer to the absolute truth. It perfectly demonstrates that a proper research design is essential to control mistakes. You cannot always eliminate sampling error, but you can absolutely control human error through rigorous planning. To visually reinforce what we have just learned and proven, let us look at this flow chart comparing the two approaches. On the left, you see the chaotic process without a research design. Notice how the arrows tangle wildly between the idea, the data, and ultimate confusion. Along the way, time and money are bleeding out as waste. Now look at the right side, representing the structured process with a research design. It is a clean, linear path. You start with a research problem, move to the design blueprint, proceed to data collection, and arrive smoothly at a clear conclusion. This diagram perfectly captures why the structured approach saves resources and guarantees reliable results. We have covered a lot of ground today, so let us summarize the key takeaways. First, the need for a research design cannot be overstated. It is the foundational pillar of any successful scientific inquiry. Second, it acts as a master blueprint that ensures you collect the right data and spend your resources wisely. Third, as we saw mathematically, it drastically increases research efficiency and minimizes non-sampling errors. Ultimately, a strong research design is exactly what separates a chaotic, biased guess from a reliable, scientifically proven fact. Thank you for watching, and you are now ready to design your own rigorous research studies.